So, welcome back friends. So, we have been looking at Lorentz group and its properties of the Lorentz group. So, we are looking at how we started with the Lorentz, how the Lorentz transformations form a group. So, if you have, so we started with saying that Lorentz transformations, which are essentially say represented by lambda. So, we looked at all the four properties of the group, which are essentially closure, associativity, existence of an inverse and existence of an identity essentially, and maybe in the reverse order, existence of an identity and then existence of a inverse. And we showed that this group is called SO31, which corresponds to keeping the line element not x1 square plus x2 square plus x3 square plus x4 square invariant, but something like x1 square minus x2 square minus x3 square. So, there is a sign difference. Okay, there is a sign difference in the line element essentially. So, that was the reason why it is called SO31. Okay. Now, then we started looking at various properties of Lorentz group essentially of this Lorentz transformations. So, we showed that two Lorentz transformation also form a Lorentz transformation. So, it becomes a group. So, group of all Lorentz transformations is a SO31 group essentially, and we tried to show that it forms a group because any two Lorentz transformations, product of them will always also, okay, any two Lorentz transformations, the product of any loop will also form a Lorentz transformation. So, the product of any two Lorentz transformations is also a Lorentz transformation, and then we looked at the closure, and that is the closure identity, and then we looked at the existence of associativity. Associativity is simple because you can easily see that the order of Lorentz transformations, they may not be commuting with each other, because as we have seen, we will see the generators and everything in a second. They may not be commuting with each other, but they are associative essentially, because it does not matter whether you multiply these to lambda 1 lambda 2 first and then with a lambda 3, or lambda 1 into lambda 2 times lambda 3, as long as the order is the same. Okay, as long as the order is same. So, associativity is valid. Then we said that there exists an identity Lorentz transformation, which is nothing but your identity element essentially, which is nothing but the eta mu or the g mu, which is unity essentially, which is a unit matrix. So, you can think that Lorentz transformations always can be thought of as a unit starting with the unity, and then for every Lorentz transformation there is also exist an inverse such that it goes back to for every Lorentz there also is such, so it just goes back to a transformation of this type, essentially lambda inverse whole transpose G, lambda inverse is equal to G. So, such that there is so lambda inverse times lambda is always equivalent to eta mu or the unity matrices and delta mu essentially. So, the set of Lorentz transformations forms a group. This is what we have seen, and then we looked at some features of the Lorentz group, that Lorentz group contains two main parts, which is essentially the boost and the rotations. In addition to boost and rotations, it also contains two discrete symmetries, which are parity and time reversal. So, time parity is x goes to minus x, essentially the space inversion is called parity, and rotations is time reversal essentially. So, this is parity essentially, discrete symmetry, space inversion p of x0, which is, this is time reversal, this is space inversion. So P of x0 goes to okay, no, this is, sorry, this entire thing is parity, okay, under which parity the operator P. So under P x0 remains x0, whereas P of x bar picks up a minus sign essentially, which is gives it like space inversion, and then you see that P transpose G P is also equivalent to G, where G is any element of the Lorentz group. So P is any element belonging to the Lorentz group essentially. So and then space inversion is or time inversion. Now this is space inversion, whereas time inversion is it changes the sign of only x0 and keeps x bar completely intact. T of x0 is equal to minus x0, T of x bar is equal to x bar essentially. So this is represented by a matrix with minus sign on the top, essentially 0 0 0 0 and T of x0. Okay. So in total you have Lorentz transformations to be written in terms of boost, rotations, parity and time inversal. So this entire set of transformations form a group essentially, and then we can classify Lorentz transformations into proper orthochronous or improper proper or improper or orthochronous or non-orthochronous. Okay. So this classification tells you that if the determinant of the Lorentz transformation is positive, then it is called a proper Lorentz transformation, and if the determinant of Lorentz transformation or the matrix which represents the Lorentz transformation is negative, that is called an improper transformation. So these are the two classifications, and then we also looked at the lambda 0 0 element essentially, and we saw that the lambda 0 0 element given by this main condition. The main condition is again this essentially, that the metric should be invariant under Lorentz transformations. Using this same condition you also have condition on not only the determinant of the Lorentz transformation but also on the lambda 0 0 element. The lambda 0 0 element, as you can see, can either be positive or less than or greater than or equal to 1, or negative and less than or equal to minus 1 essentially. So it can be either positive and greater than or equal to plus 1, or negative, which can be and negative and less than or equal to minus 1. So using these two we have another classification of the Lorentz transformation, that if it is lambda 0 0 element is greater than or equal to 1, it is called orthochronous, and lambda 0 0 element is less than or equal to minus 1, it is called non-orthochronous. So using this thing, all Lorentz transformations can either be proper, improper or orthochronous or non-orthochronous. Okay. So let's look at some classification. So P is proper, improper and non-orthochronous because its determinant is minus 1, because it is 1 minus 1 minus 1 minus 1. So its determinant is minus 1, so it is improper, but it is orthochronous because lambda 0 0 element is positive. T is improper, its also determinant is minus 1 because it is minus 1 times 1 1 1 1. So it is essentially again odd number of 1s times a minus 1. It gives you it is an improper Lorentz transformation, and it is also non-orthochronous because lambda 0 0 element can be is equivalent to minus 1. Okay. So now what we have seen is that all the proper transformations form a group, all the orthochronous transformations form a group, all the orthochronous transformations, and then all the proper and orthochronous intersection essentially form a group. This group contains the boosts and rotations, essentially this is what we are interested in. Altogether, proper, orthochronous, improper, and orthochronous also form a group essentially. So these are the various subgroups of the Lorentz group essentially, and then in terms of the transformations, we can classify them as proper, improper, or chronos, orthochronous, or non-orthochronous set of Lorentz transformations. With this backing, essentially, so we started looking at boosts and rotations. They are proper and orthochronous transformations of the Lorentz group. With this, we started looking at infinitesimal Lorentz transformations. So we have a small modification with respect to eta mu nu essentially, or g mu nu, which is the metric tensor essentially, and then we imposing the condition that the metric tensor is invariant under Lorentz transformations. We have that this omega mu nu is a small modification to the eta mu nu, to the eta mu nu or g mu nu to g mu nu. We immediately see by a simple transformation of if I as a infinitesimal transformation of the metric tensor should give you back your Lorentz transformation, or this is essentially unity. So minor modification of the unity should give you Lorentz transformation. You see this modification is a tensor or a matrix, it should be an antisymmetric matrix essentially, because you can show that it should be this at order omega square, it should reproduce your metric. So this gives you that the metric should be the matrix omega should be antisymmetric, and this puts some conditions upon the matrix. It's a 4 by 4 independent antisymmetric matrix. So the number of independent entries are only 6 essentially. Okay, there are only 6 entries, and so we have explicitly written down all the 6 matrices which are possible, and we see which are boost. These 3 W omega 01, omega 02, omega 03 are boost. W12, W omega 12, omega 13, omega 23 are the rotations. Okay, now we did some small modification, and we can re-express everything in terms of some matrix essentially M. Okay, alpha beta. Okay, so these matrices can be written in terms of some M alpha beta times omega mu nu, where omega mu nu is given by this particular fashion. Okay, and so these omega mu nu, M mu nu are essentially generators of boost and rotations. They are end up being the generators of boost and rotations. So we have written the corresponding matrices of boost and rotations. So the only thing is that we have to define correctly what are the boosts and what are the rotations, and okay, and then we get these following commutation relations, which shows that 2 boost essentially 2 boost give rise to a rotation, 2 rotations are closed themselves, essentially they form a closed algebra. Whereas a rotation and a boost gives you back a boost essentially. It's a rotation and a boost can be expressed in terms of a boost. So we have set up the main thing that how to write down the generators of the Lorentz group, and we, as a promised, we said we have written in terms of generators of boost and rotations. Okay, which is very well nice. So the L's are generators of rotations, they form a closed algebra. So 2 rotations, they are independent of boost, they form a algebra of their own, so they form a subgroup of the Lorentz group completely on their own, which is SO3. The boost do not form a group on their own. I think this we mentioned earlier also, but because two rotations goes back to one rotation, I think this is something, these bunch of commutation relations everybody should remember, and they should always, I don't say it should be by hearted or something, but they should always appreciate this fact that two boosts always go to a rotation. So this is important, and I can tell you that it will be also one of the questions in your exam essentially. So whether two boosts give you a rotation or whether the rotations forming, it will be related one of these questions essentially. So this is important that you guys you remember this and understand this and appreciate this fact essentially. Now from these generators, from the infinitesimal generators, one can form finite from infinitesimal generators. So this is exactly like for rotations, for the rotation group. So we have written every group element A is equal to e power I theta times generators of rotation x bar essentially. Exactly theta 1, theta 2, theta 3 are the rotations. Theta cap is equal to theta 1, theta 2, theta 3. Theta 1, theta 2, theta 3 are rotations in xy plane, yz plane, and so on. So whereas x is nothing but the generators of infinitesimal rotations. Putting these two together, we showed that this forms every group element of rotations. Can be expressed as follows essentially. So you can have this expression, so where every group element is expressed in terms of exponentiation over generators and theta essentially. Now we know the we know the what do you call the commutation relations between the generators. They are non-commutative, they go back to themselves essentially, and that gives you the finite every group element. In the same way, in the same manner, we can give which we have written already, the cos and sine are expressions essentially. So we can do the same thing. So in general, for a Lorentz transformation, a general Lorentz transformation, sorry, a general Lorentz transformation can be expressed as, guess, very simple, is equal to lambda is equal to e power xi I k I plus theta I Li. As simple as this. Okay. So this is equivalent to, now why this is the case, because we know xi's are k's are generators of boost, generators of rotations, and xi's are the parameters, the rapidity parameters xi's are, and thetas are the angles essentially of rotation. Xi's are the rapidity parameter, there are three of them. So you can also express them as e power xi bar dot k bar plus theta bar plus L bar. Okay. Now, or you can express in the original format essentially in terms of e power half omega mu nu m mu nu. Okay. Now, omega mu nu sometimes it's also called now okay, can be written in terms of omega mu nu, and we will see that omega mu nu becomes sigma mu nu the case of the Dirac equation essentially, as we will see. So now we have this Lorentz group and we have seen these things. Now the important point is that the representations of the Lorentz group are essentially your particles essentially. So the representations of your Lorentz group are your particles. To be more exact, so the Lorentz group is represented every lambda, every Lorentz transformation has this particular fashion. The representations particles okay, one can okay, this statement is not exactly accurate. The exact accurate statement more accurately the representations of the Poincare group are the particles found in nature. We won't do a great detail of the Poincare group. I'll just mention what is a Poincare group. Poincare group element essentially, or a Poincare transformation is is okay is, so if you call Poincare a transformation as lambda tilde, mu is equal to lambda mu plus a mu. That's it. So it has translations. Say Poincare group is nothing but Poincare transformation is equal to Lorentz transformations plus translations. How many generators are there for Lorentz transformation? There are 6 generators. 10 is equal to 6 plus 4, because a mu has 4 generators, because a mu is equal to a0, a1, a2, a3, a4. It's a Lorentz vector. So there are 4 generators. So the total number of generators of the Poincare group are essentially 10. So it is now that comes more in the realm of quantum field theory, that the all the particles found in nature are essentially representations of the Poincare group essentially. That's the basic assumption. Now that is one of the first lectures one would listen in say in relativistic quantum field theories. Okay, but for us what we want to see is essentially how different particles transform under the Lorentz group essentially. Different kind of particles transform under. One of the first particles which transforms are scalars. How do scalars transform under Lorentz group? Scalars are invariant so these are particles or scalar wave functions, okay, because we are concerned more with wave functions, okay. We won't go into the quantum field theory interpretation as of now because we have not introduced you particles and fields and so on. So we'll deal with the wave functions. So how does a scalar wave function transform? The scalar wave function is like a Klein-Gordon wave function which we have seen. So Klein-Gordon wave function. So the Klein-Gordon wave function, okay, is nothing but what's phi. We had represented it as phi. Now phi is invariant under Lorentz transformations because it doesn't have any index. It doesn't have any index. It doesn't have so it doesn't have any index. So that means what I mean, it is not phi I or phi mu or anything, it doesn't have any index, so it doesn't so phi of x is invariant under Lorentz transformations. So its equation, its wave equation is made up of invariant quantities, like for example box plus m square times phi is equal to 0. Its wave equation is made up of invariant. So box is a Lorentz invariant because it is del mu, this is equal to box, this is equal to a scalar under LTs essentially under Lorentz transformations. So this is an invariant quantity. M square is an invariant, it's a scalar quantity, again it doesn't have any, it's not a vector, it's not anything, it's a scalar quantity, so it's invariant. So the Klein-Gordon equation is by definition, you construct it with directly with invariant quantities, and the solution, the wave function is also an invariant quantity essentially under Lorentz transformations. Now let's consider vectors. What are vectors? We have not introduced, we have introduced vector particles, vector fields in terms of one particular aspect essentially, which is called a mu. So we introduced vector potential. Okay, as vector potential as essentially a combination of scalar potential and a bar essentially. So which is the vector potential. So vector potential, it's a 4 vector potential. So as we introduced this as a part of the scalar potential and everything. This is what we used to couple it with for the Klein-Gordon field essentially. Okay, when we are coupling the Klein-Gordon field with the electromagnetic field, this is what we used. Now how does this vector potential vectors transform? So how do the vectors transform a prime, a mu prime under Lorentz transformations, a mu, lambda mu. Now a mu of x. Okay, you see it transforms exactly like x mu, any other 4 vector. Like p mu, x mu, etc., etc. So a mu also transforms like a like a 4 vector under Lorentz transformations. So it is a vector. So what we call it as is a vector under a Lorentz transformation. So A mu is like a vector. Anything with one index is a vector. J mu, for example, is a vector. So we have J mu also a vector, and so on. So essentially, there are all these quantities which you have been introduced essentially. P mu, A mu, X mu, J mu. Okay. Now question. So we have seen these two fields, these two wave functions so far. What about, how about psi? Dirac wave function. The Dirac wave function, okay, the Dirac wave function transforms as a spinor under Lorentz transformations. Now this is what we have been trying to get it to essentially. How does the Dirac wave function transform? Essentially, the Dirac wave function transforms as a spinor under Lorentz transform. Now there is no spinor index so far we have seen. We have not seen that spinor index at all essentially so far in our definition of Lorentz transformations. So how does it transform? It transforms as a representation of the Lorentz group essentially. It transforms as a representation of the Lorentz group in spinorial space. Now what is spinorial space? It's a wave, okay. We have seen that any represent, okay. We have not seen any spinor index no so far. So we have not seen the Dirac psi I or something essentially. So it transforms as a representation of the Lorentz group, okay, in spinor space, spinor vector space. Now is such a thing possible? Yes, it is possible because SO31 is isomorphic to SU2 times SU2. Accurately it will be Z2. Accurately it is SO31 is related to SU2 times SU2. It's a direct product essentially by Z2. Okay, Z2 I will introduce what is Z2. And SU2 is a spinor space which we have known essentially. We know that it's a complex vector space of SU2, and they have spinor representations essentially. So their fundamental is a spinor representation. Same thing as an SU2, which is another spinor representation. So these two combined with some Z2. Z2 is nothing but parity essentially in this case. This forms a Dirac representation. It forms a representation of the Dirac. Now, so with all this background, now we have come to the crux of the problem that the Dirac spinors transform as Dirac spinor transforms under a representation of the Lorentz group, which is called SU2 times SU2 by Z2 essentially. Okay, so we'll stop here. And in the next class, we'll continue on this essentially, and we'll look at how the Lorentz, the Dirac spinor transforms and why it is called a spinor, and then we look at the solutions of the Dirac spinor essentially. So let me stop here, okay, and thank you very much. Welcome essentially.